Good evening, everyone. My name is Andrew Fracknoy. I'm the astronomy professor here at Foothill College in Los Altos Hills, and it's a great pleasure for me to welcome everyone here in the Smithwick Auditorium and everyone watching us on the web to this lecture, this very special lecture in the 16th Annual Silicon Valley Astronomy Lectures. This program, like the others, is co-sponsored by 4 wonderful organizations: NASA's Ames Research Center, the Astronomical Society of the Pacific, the SETI, or Search for Extraterrestrial Intelligence Institute, and the Foothill College Astronomy Program, and we're very grateful for their help. Tonight's program, which as usual presents the latest developments in astronomy in non-technical language, is being presented to us by Dr. Jeff Moore of NASA Ames. Dr. Moore is a research scientist in the Space Science Division at NASA's Ames Research Center. His research has focused on the geologic evolution of the landscapes and crustal materials of other planets. His published work explores the roles of impact cratering, of things that hit, volcanoes, things that explode from underneath, and tectonism on terrestrial planets and the outer planets' satellites. So the worlds near us are called the terrestrial planets, and then the moons, the solid moons in the outer solar system. Dr. Moore is the leader of the imaging team for the New Horizons mission, which recently went by Pluto, and has worked on the Mars Exploration Rover, the Mars Reconnaissance Orbiter, and the Galileo mission to Jupiter, among others. He is the recipient of the 2013 Distinguished Scientist Honor Award at NASA Ames, and someone who has a long history in explaining the recent developments in planetary science, not just to his colleagues, but to the public. And I was delighted to see him at the press conference where they were announcing the latest sexy results from Pluto, and have him be the one explaining some of these wonderful slides to us. So it's a really great time in astronomy. Imagine if we could have been there when Columbus first unveiled news of the New World. Imagine if we could have looked through Galileo's telescope when he first pointed it to the heavens. We can't do that, but we are privileged to be alive at the time when we are first exploring Pluto and making it not just a small blip in the sky, but a real world for exploration. I can think of no better guide to our journey than Dr. Jeff Moore.
Good evening, everybody. Well, although my name is the only name on the slide, of course, I'm sure you all know that the reality is that there are hundreds, if not several thousand people ultimately to thank for the success of this mission. And of course, the taxpayers who paid for it. So this is a nationwide enterprise. In fact, more properly, it should be thought of as a planetary-wide enterprise, which I simply have the honor of discussing the geology results as we know them a few months after the encounter. Okay, so let's put things in context. We're going to talk about objects in the Kuiper belt. The Kuiper belt is kind of a third region of the solar system. The inner region of the solar system, as you heard Andy say, are the terrestrial planets, which we live on one of them. And then beyond that are the 4 gas giants and their suite of icy worlds. And then beyond that is this zone, the third zone of the solar system, the Kuiper belt, which is made up of, an uncounted number of objects, many of which, of course, are very small, but some of them are quite large. They're, planet size or dwarf planet size. Pluto is the largest known Kuiper belt object, although Eris is almost as big. And these Kuiper belt dwarf planets or planets often have moons. Pluto has Charon, which is half the size of Pluto, and many of these other dwarf planets also have moons. So that's putting things in context of what we're going to talk about tonight, the first mission to the third zone of the solar system and the results from an encounter with its premier target. Okay, so Pluto was discovered almost exactly 86 years ago. It was photographed and plates taken in January and February of 1930 by this gentleman, Clyde Tombaugh, who was a self-taught kid from Kansas. He built his first telescopes using spare parts from farm equipment and ground his own mirrors. His skills as a technician were recognized by the Lowell Observatory, and they hired him to use this telescope, which is not much bigger than probably telescopes you can find at amateur astronomy clubs, but it's especially designed to take photographic plates. And he used this telescope to take these plates, and which in these are the discovery plates. You can see this is a bright star and that's a bright star, but you see this little dot there has moved to the other side of the star in this next plate. Those are the discovery plates of Pluto. So that's how Pluto was discovered. So they of course, took a number of other images tracking Pluto for a few weeks, and they calculated its orbit and determined that it was indeed orbiting in a strange elliptical orbit that was also tilted to the main plane the rest of the planets orbit in. And it was, at the time, identified as the 9th planet of the solar system. And of course, those of us on the imaging team still think of it as the 9th planet. So, even if Mike Brown is right and he has found yet another planet, it will be the 10th planet, I just like to say. So, okay, so what did we know leading up to the encounter with Pluto? We knew by the 1980s that Pluto had quite a range of brightnesses, from very bright to very dark surfaces, and quite a range of colors. We knew that it had weird surface markings, as you can see from these images taken by HST. These are, in fact, represent the highest resolution images we have had of Pluto until just last summer, to give you a sense of how we've gone from knowing very little to, as you'll see, knowing quite a bit, or at least having a lot more information to work with. We also, that's always strangenesses with PowerPoint, isn't there? Okay. So Pluto was discovered to have a large moon back in 1978, almost 40 years ago, by Jim Christie. Here's the discovery image. A higher resolution image gives you a real sense of the separation of the two objects. As you can see, it's about 12,000 miles separates the two objects from each other. They face each other, so one face is always facing the other face as they go around each other. They have a period, and thus they have a day that's a little longer than 6 Earth days. And this, in the last decade, using Hubble telescope observations, we discovered 4 more much smaller moons. We discovered Nix and Hydra first, and then more recently we discovered Styx and Kerberos, and they literally show up as little dots next to the size of the much larger Charon and Pluto. But put things in perspective, Pluto's about the size of the Earth's moons, and Charon's half that size. Okay, so people began to speculate about how did the planetary moon system of Pluto form, and the least obnoxious explanation modelers have been able to come up with is a giant impact origin. It was first suggested in the 1980s. Numerical models seem to be incapable of producing Charon by any other means, so much in the same way we think the Earth's moon was formed from the Earth by a large impact, a similar event took place early in solar system history, spinning off Charon as well as smaller fragments which became the other moons. And in fact, this point is made in this last bullet that the giant impact hypothesis was strengthened by the discovery of the smaller moons. We also knew throughout the 1980s and 90s and into the last decade that there was a lot of interesting ices, volatile ices on Pluto. We knew there was carbon monoxide, there was methane, and there was nitrogen. We also discovered that there was water ice, H2O ice, on Charon, but we weren't seeing water ice spectra on Pluto from Earth-based or from HST-based observations, although we had theoretical reasons to believe that there probably would be a lot of water in the crust of Pluto. And so it was clear that there were these interesting 3 volatiles. They all evaporate at different temperatures. They have different densities and so on and so on. And we anticipated this would result in some interesting landscapes on Pluto, and as you'll soon see, it did. We also discovered back in 1985 that Pluto had a thin atmosphere. We weren't quite sure how thick it was. We knew it was substantial. It was a permanent atmosphere, although there's the possibility it could freeze out completely during Pluto's very long winters, when Pluto's much further from the sun than it is when it's near the sun. It has, as I said, an elliptical orbit. The observations that were made before New Horizons got to Pluto suggested the atmospheric pressure might be around 10 microbars. 1 microbar is 1/1,000,000th the Earth's atmospheric pressure, so 10 microbars is 1/100,000th of the Earth's atmospheric pressure. And we also calculated that probably, and they also knew this atmosphere was mostly made of nitrogen, and we speculated that probably over the lifetime of the solar system, maybe 2 or 3 kilometers, 1 or 2 miles of nitrogen ice had sublimated off the surface and been lost into space. So we also anticipated we'd see interesting landscapes or the consequence of the loss of nitrogen ice over the lifetime of the solar system. Now, people think of Pluto as an icy world, and most of the landscapes I'm going to show you soon are, in fact, all made of different kinds of ice. But we should always bear in mind that Pluto is mostly a rocky, not an icy body, that the density of Pluto is around 2 grams per cubic centimeter, roughly speaking. And so we know that the bulk of the interior is made up of silicate rock, just like the crust and mantle of the Earth is, and that there may be a little liquid layer sitting right above the rocky core, and then above that is probably a thick water ice shell in which there's a veneer of the methane and nitrogen and carbon monoxide ices that we can see in spectra. And of course, I also want to mention that it's important to remember that we believe that there's the usual relative abundance of radiogenic elements, thorium, uranium, and potassium, which are giving off heat as they undergo radioactive decay. And this meager heat produced by the interior of Pluto, as we will see, maybe have been sufficient enough to drive some of the internal processes we see that are expressing themselves with internally formed landscapes on Pluto. So the fact that we're dealing with these very, very cold, easily volatilized ices means these very meager temperatures may be sufficient to cause geological evolution. Okay, so our mission was selected by NASA in 2001, appropriately. We built the spacecraft mostly at the Applied Physics Laboratory in Laurel, Maryland, and it was launched on 19th of January 2006, just slightly more than 10 years ago. We launched it on the largest rocket that you could at that time acquire in the booster stable that the United States had at its disposal. This particular rocket is an Atlas V. Usually this cowling here holds a school bus-sized communication satellite that's to be launched to geosynchronous orbit, but we didn't use it that way. Instead, we put another solid rocket motor in this, and our spacecraft, the New Horizons spacecraft, is about the same size as a baby grand piano. So it was basically a hood ornament in the very tip of this. And we took full advantage of that. So we basically, you all know the momentum equation where you can trade mass for velocity. So by having a low mass spacecraft, we could go much, much faster than it takes really to launch something into geosynchronous orbit. And in fact, at the time that the spacecraft left Earth's orbit and began its journey towards Pluto, it was the fastest object ever to leave Earth's orbit, man-made object to ever leave Earth's orbit. It crossed the orbit of the moon in 10 hours, and put that in perspective, it took the astronauts 3 days to get to the moon. Here I can show you our trajectory. Whoops, I'll show our trajectory, and we'll go back to what the spacecraft does. So as I say, we launched in 2006. Only 13 months later, we flew past the Jupiter system. We got some very interesting results, which I think have been reported in this forum before. And then we flew past Pluto last July. So let's go back and look at our spacecraft. Now, we have several instruments on it, and some of them I'm going to barely mention because the SWAP and PEPSI instruments are fields and particles instruments, and I'm not a fields or particles physicist. I'm a geologist, so it's not really my expertise. I can certainly recommend people you can talk to. You want to know what these instruments saw. I'm a geologist, so I was mostly interested in what the spectrometers and the cameras saw. So here's the LORRI camera, which stands for Long Range Reconnaissance Imager. It's our telephoto, narrow angle, black and white framing camera. And then this instrument here, which looks like it has a flat hat on it, is RALPH. And RALPH is a single set of optics which split off the light coming into it, and the shorter wavelengths are sent to MVIC, which stands for multispectral imaging camera, which is our medium resolution wide angle color camera. And you're going to see a lot of pictures from MVIC. You're going to hear me talk about INVIC. All the color pictures you're going to see are mostly INVIC pictures, with the exceptions of things which are being color-coded by their composition, which is information we got from LISA, which is our imaging spectrometer. Okay, so Pluto's spin axis is tilted somewhat towards the sun. It's not perpendicular to the plane in which it orbits around the sun. And that had the effect of, at least during this particular epoch, which we had an encounter with Pluto, that Pluto is tilted about 45 degrees to the direction of the spacecraft's travel. So it was more like shooting through a bullseye than it was, encountering one object sequentially. And that had the unfortunate effect of meaning that we were close to everything almost simultaneously, and that made planning the encounter pretty tricky because everything that you wanted to see was already there all at once. But we put together a very clever and successful encounter plan. I will now show you some of the results from that. Okay, so here is the highest resolution global color images from INVIC, which you heard me mention before. These show the two targets, their relative sizes to each other. Pluto is indeed almost twice the size of Charon. And of course, by the nature of the encounter, this is the hemisphere that faces Pluto. And you'll hear me refer to that sometimes as the sub-Pluto hemisphere. And this is the anti-Charon hemisphere, the hemisphere which if you were standing on it, you could never see Pluto. So you can't have it both ways. You can pick the sub-hemisphere of one target. You'll get the anti-hemisphere of the other target with this particular encounter sequence. This is the first view we got that really gave us an idea of how impressive and extensive the atmosphere of Pluto was. We took this picture a few hours after the encounter and looked back. And so this is basically being silhouetted more or less against the sun. It's not really an eclipse picture, but it's a situation where the sun's probably off here somewhere. It's really interesting that if you were standing on Pluto, the sky would be blue. So the atmosphere has a blue tint to it, but in detail, what are you looking at? I just told you the atmosphere is only 1/100,000th the thickness or the density of the Earth's atmosphere. So the reality is, you look more closely, and this is a picture taken a few hours earlier, and this is a small section of an image that was a much bigger crescent. And so you're still, here's still the terminator, and you can see that, in fact, the atmosphere is made up of a series of discrete layers. And it is these layers which make the atmosphere bright. And so what are the layers? The layers are basically smog. They're made by the fact that there is a little bit of methane in Pluto's atmosphere, and the methane is irradiated by sunlight and cosmic rays and so on and converted into heavier hydrocarbons, and they basically become little solid particles smaller than cigarette smoke particles, and they lie suspended in layers above Pluto's surface. They slowly settle out, and they're constantly being produced. Now, here's what I like to call psychedelic Pluto. And psychedelic Pluto is made using a process called principal components analysis, which I won't torment you what that means. But what it does is that it looks for color variation. So these aren't the different colors of Pluto, but what the colors have been assigned to is to show how one place has a different color than another. So this is showing you the dynamic range of color, or how many different colors there are on Pluto. I mean, the reality is, if you were to see it with naked eye, it would kind of look beige. But if you use all four of your color channels that we have on INVIC, you can show that there is a lot of color diversity on Pluto, which in turn suggests there's a lot of stuff going on Pluto to give it that appearance. Okay, now let's talk about some of the results from the LISA spectrometer. First of all, let's talk about methane ice. I just want to point out a couple of places where methane ice is really prominent. They're really prominent here along these features, which I'll show you shortly, which are referred to as bladed terrain on top of Titardus Dorsey. You can see how dark purple the methane signature is here. And also I want to show that there's this set of cliffs, and we'll look at the cliffs much more closely here in a moment. And the plateau behind the cliffs, made up of, which we've informally called Vega Terra, you can see there's a strong methane signature up above the cliffs. And also there's quite a bit of methane here in the Arctic, the North Polar region of Pluto. Nitrogen is kind of everywhere, but it's particularly prominent in Sputnik Planum, and we'll discuss the implications of that in just a moment. That's the real take-home message from this, is that there's a vast amount of nitrogen in Sputnik Planum, and you can see it does also form kind of a ring here at around 45 degrees north. There's carbon monoxide gas, or ice, I should say, carbon monoxide ice. And it really, for all intents and purposes, is really only seen as a component of the two ices which make up Sputnik Planum. In fact, it's the only place you can really see it on Pluto is in Sputnik Planum. But we think it's actually a relatively small component. We suspect that Sputnik Planum's deposits are dominated by nitrogen ice. And last but not least, and as I told you, based upon observations we'd made before New Horizons flew past Pluto, we'd never seen ice, water ice, but we now are seeing water ice. In particular, we see water ice here in the dark regions, like this region informally called Cthulhu Regio. And I'll show you this big fracture system better, but the walls of the fracture system are also have a strong water ice signature. And that's consistent with the idea that the crust of Pluto is dominated by water ice, that the methane and nitrogen and carbon monoxide are veneers. In some cases, they may be several miles thick, but the bulk of the crust is made up of water ice. And also, water ice is far stronger than the other three ices I have mentioned. Water ice can support several kilometers worth of relief, whereas the other ices either can support basically no relief or might at best support a few hundred meters of relief. Okay, so as I say, I'm a geologist, so how did we start this process? Well, what we did first was we simply looked at the pictures and identified all the different kinds of landforms, and we asked ourselves, is this landform like that landform? If yes, give them the same color. If no, give them a different color. And we kind of systematically went around the images that had resolutions high enough to make out the landscape and assigned them just landform types. And we knew we were finished when the whole map was colored. It's kind of like kindergarten, right? And I want to emphasize this is not a geologic map. This is simply a landform identification map. So we started with identifying what are all the landforms, what's the variety of landforms on the planet. Then having done that, then we began to ask ourselves questions like, looking at the landforms, what processes could have formed those landforms? And the other thing we did was we began to look at how the landforms relate to each other. I mean, are some things setting on top of other things? Do some faults cross some features but not other features? Are there craters which set on top of one type of material but has been embayed by another type of material? We used that process to figure out the stratigraphic order of the features on Pluto and be able to say, what's on the top of the deposits, what's on the bottom of the deposits. The bottom of the deposits are thought to be older. The deposits on top are thought to be younger, so we can sort out the geological history of Pluto. So while the last image I showed you is not a geological map, this does begin to be a geological map. And in particular, this is the region Sputnik Planum. It's about the size of Texas. We think it's mostly made of nitrogen ice. We think it may be several miles thick. We don't know how thick it is, but it could be 5 miles thick for all we know. It's very complex. I'm going to show you some images and pictures of it here in a moment. One thing that caught our attention right away is that there are these blisters out on the surface. We think those are a likely signature or topographic signature of uplift due to solid-state convection. Solid-state convection is very analogous to looking inside a pot of slowly boiling porridge or oatmeal and seeing the cells of stuff rising up, spreading out, and sinking. Lava lamps, basically, are examples of convection. And this image here at the bottom, in fact, is a computer model that one of our researchers has produced, simulating what we think is how this convection pattern looks at depths. So these things are like 20 to 30 miles across. We think that they are standing in a region that might be 5 miles deep of solid nitrogen, and we think that what's warming them is the radiogenic heating I mentioned earlier from the large rocky interior of Pluto. There's a lot of interesting cellular forms and other textures on Pluto. There's on Sputnik Planum, there is pitted plains, which We've just recently acquired new pictures, which unfortunately I don't have a lot of them to show tonight, but it's covered with pits. We think the pits are formed by sublimation. Sublimation is a process where ice directly turns in or directly evaporates into a gas without going through a liquid phase. We'll be talking a little bit more about sublimation in a moment. There's the cellular terrain I just mentioned. Right here along this region here, there's dark flow patterns where it looks like the nitrogen ice is flowing into embayments and embaying up against the scarp, which makes up the large topographic basin in which Sputnik Planum sits in. I should mention that the topographic basin we suspect is a very ancient, very large impact basin. Considering that all the other geological features set in or on top of this topographic basin means the topographic basin is amongst the oldest, if not the oldest things we can recognize on Pluto. So some huge primordial impact formed the basin which we think nitrogen ice has exploited. Now I need to tell you that about nitrogen ice. Nitrogen ice has the mechanical consistency of silly putty, or that's probably as good an analog as I can pick. It won't support much topography. It might support a few meters worth of relief. It will, over time scales of a few months or years, flow. So it acts almost as if it were a liquid, although it is simply a soft, easily deformable solid, like I said, like silly putty. So think of silly putty. It has one other interesting characteristic, and that is that it is denser than water ice. And that has a very interesting consequence for the appearance of Pluto, that while water ice is very strong and it can hold up several miles worth of topography, you see mountains or big scarps or things like that or cliffs or things like that on Pluto, you have to assume that they're miles high. They have to be mostly made of water ice. But the water ice is less dense than the nitrogen. So what's going on is we think nitrogen has, over the lifetime of Pluto, flowed over the rim of Sputnik Planum and into the interior. And because the water ice is lighter than the nitrogen ice, we think the water ice has actually been lofted and floated and transported buoyantly, off the rim and in some ways into the interior of Sputnik Planum. Now this is color-coded based upon elevation, so we have a technique that we take images from different viewing geometries, just like stereo viewing. In fact, it is stereo viewing, but we have methods which we can derive using the formal rules of trigonometry and geometry to determine the heights of things. And we do that to generate this coloration, which I hope you can read that scale. Unfortunately, I know it's in the metric system. So 6 kilometers is like 4 miles. And you see there's a range of 4 miles worth of relief from the highest peak to the lowest portion of the rim around Sputnik Planum. And so we think that, for lack of a better term, you can think of these large blocks of water ice out in Sputnik Planum as basically glorified icebergs floating, if you will have it, in this soft plastic nitrogen ice. Also, because nitrogen ice is so soft and deformable, we have evidence for pitted uplands and valley glaciation. So if you can see in this image that from this landscape, which we think is its funny pitted uplands appearance is due originally to sublimation, where material that was up there has sublimated away. But also solid nitrogen is collecting and running down slope. It's passing through these gaps labeled, this one's below this B and the other one's above this B, and flowing out onto the surface. So this big blob that's surrounded by the red arrows is a blob, a glacier, if you have it, of nitrogen ice that's flowed out into Sputnik Planum. And this same region here was taken about 45 minutes later at a much higher lighting, and you can actually see the flow lines much more distinctly in this image than in this image that show this process of producing basically glacial deposits out in Sputnik Planum. Well, before we leave the Sputnik Planum region, I have to really tell you about some strange things that we saw. That we actually saw them in the very first pictures we got down, but we looked at each other and thought, we're not going to say that. We're not going to use the V word. Because we didn't really expect to see volcanoes. We certainly didn't expect to see volcanic mountains on Pluto. There aren't really good examples of or any examples that I know of tall volcanic ice mountains on ice worlds. Now, we all know that, for instance, Saturn's moon Enceladus has eruptions, but they erupt out of fissures. They don't produce, topographic constructs. But we looked at the surface, and we saw one of them is just beyond the terminator, but was illuminated by the twilight that you saw from the hazes in the earlier picture. So twilight illumination provides us with this scene, and we took it from several different viewing geometries, so even with twilight, we were able to still derive topographic maps. And again, this is color-coded the same way the map I showed you a slide or so ago of the icebergs of Sputnik Planum. We could tell you that, that, for instance, this feature here, Right Mons, is about 2 or 3 miles high. It has a central depression or crater in it that's about 1 or 2 miles deep. Likewise, this is another feature, Picard Mons, which is larger and even deeper. Especially when you look at Right Mons, which we have good high-resolution coverage for, you can see it has this weird ropey or concentric texture about it. It doesn't look like it's made by any kind of erosional process. It almost certainly has been made by some sort of constructional process. So it has to be either volcanic or made by tectonic forces or something like that. And I have to say that, it's the best candidate for volcanic features we've seen on Pluto, or for that matter, any place in the solar system where you have a tall mountain made of ice. But of course, this begs the issue. I've been able to say we can use the the little bit of warmth that comes out of the interior of Pluto to drive soft, very volatile ices like nitrogen. It's hard to understand how something which is several miles high, which would have to be made out of water ice, how the warmth from the interior of Pluto would be sufficient to form a volcanic feature out of water ice. But given its height, it would have to be pretty much made of water. So it remains a mystery. We're still trying to understand what the heck are we looking at. But I wanted to show it to you in part to impart the sense of wonder and puzzlement that all of us on the team are still undergoing as we try to understand what's creating these landscapes. This is that same fracture I showed you a few slides ago that had the big walls that were that showed up with a strong water signal, and you can see this cliff is like almost 2.5, 3 miles high. And again, as I said before, very high, very steep cliffs have to be made of water ice. So the fact that you have these kind of steep cliffs formed by cracking and fracturing on Pluto is evidence that the bulk of the crust is made of water ice. There are a lot of these fractures and faults on Pluto. There's a whole range of orientations and states of preservation and so on, suggesting that there's been a long episode throughout much of Pluto's history that something has caused the surface to be stretched and cracked. There's also a large variety of dissected terrains of valleys, for lack of a better, I might as well use plain English, a large variety of valleys on Pluto. And both the fluted shapes and slopes of these valleys probably result from, again, the flow of nitrogen-rich ice. And if the ice can build up thick enough in the valleys, you could even possibly get some incipient melting of the nitrogen ice, and a little bit of liquid nitrogen at the base of the ice. Those two process together, moving solid ice, and if you do get a little bit of melting at the bottom of the ice, a little bit of basal melting, will operate then to carve valleys just the same way that water ice carves glacial valleys on the Earth, like Yosemite Valley, for instance. So we think that all these valleys were mostly formed by glaciers operating up on the highlands of Pluto. The glaciers don't seem to be there now, so that leads us to two possibilities: that there was once a lot more ice on nitrogen ice on Pluto than there is today, and you could sort of think of the ice sitting up on the highlands in the same way we think of the ice covering the great plateaus of Antarctica and Greenland, and they basically flow out off the edges of the plateaus, and in the Earth's case, they flow into the sea. In this case, they would have flown into Sputnik Planum or someplace, and that could have carved these features. And that could have conceivably been a one-way process. As I mentioned at the beginning of the talk, that people speculate that Pluto may have lost a couple miles worth of ice, nitrogen ice, over its history. So if this is the only way these things have formed, it would be a one-way process, that once the nitrogen is gone, there's not going to be any more, there won't be any more glaciers formed. But there's also a possibility that nitrogen vaporizes off of Sputnik Planum, reprecipitates out as snow up on the highlands, and there's basically a cycle which continues to generate new episodes of nitrogen glaciers, and so this process could be ongoing. And of course, these two processes are not mutually exclusive. They could both be happening. Okay, I mentioned Vega Terra earlier and Periplanitia, and I mentioned that Vega Terra, this region up here on the cliffs, behind the cliffs, has a methane signature, whereas the floor of Periplanitia in front of the cliffs has a water signature. We think these are cliffs that are retreating, just like sea cliffs retreat from wave action on the Earth, although we don't think wave action, of course, is what's causing these to retreat. We think what's happening is that there's a large amount of methane ice mixed into the material which make up the cliff face, and as the methane ice sublimates away, it does two things. Some of it immediately reprecipitates out on the tops of the cliffs, but as it also sublimates away, it either exposes or releases chunks of water ice, and that's why we're seeing the water ice signature down on the floor of Periplanitia. So this is scarp retreat on a large scale. See, there's 60 miles across for the scale bar of cliff retreat being driven by sublimation. Perhaps an even more exotic landscape, and you heard me mention earlier when I showed you the slide where the methane ice was seen of the so-called bladed terrain of Totardus dorsae. These blades are typically about 1,000 yards or so high. They are more, maybe up to, approximately that. They have, as I said, seen a very strong methane signature. We think one of two things are forming them. That either they began as cracks by whatever process made the ridges which they set on top of in the first place, and these cracks are simply then subsequently made wider by the sublimation of methane ice, and basically they're being shrunk down to this blade-like shape as the ice disappears. Or alternatively, it could simply be a place where methane ice is precipitating out, and the precipitation of methane ice might operate to produce very thin little ridges. We're still trying to decide which of those two explanations is correct. In the high latitudes near the North Pole, we see these ancient eroded mantled terrain which has very deep pits on them. The pits are like 2 or 3 miles deep. It's hard to understand how they form. The pits themselves may have been formed by sublimation, but then you see these deposits setting down in the pits, and we don't know if that's material that's snowed back into the pits after they were formed, or is it more ice volcanism that's percolated up and resurfaced the pits. As I say, the pits all occur at have different depths, so they aren't going down to some common level. So we remain profoundly mystified by how these pits are formed. And I, again, like so many things I've shown you this evening, I'm mainly showing them to you just to say, hey, isn't this cool? We don't know what it is yet, but there's a bit of our speculation. Let me briefly discuss the implications of the crater statistics. It turns out that we see a whole range of cratered landscapes on Pluto from places which have no craters on it, like Sputnik Planum, which means that Sputnik Planum essentially has 0 crater retention age, which in some sense could mean that it's only a few years old, or not more than maybe 10 million years old at the absolute maximum. And then we see other places on Pluto which are heavily cratered and date back to early solar system history. But then we see regions that have some craters but not a lot of craters, which mean that they were formed or otherwise altered sometime intermediate period in solar system history, not at the beginning and not most recently, but maybe 2 billion years ago. I haven't shown you Charon yet, but I will in just a moment. And even there are clearly 2 types of terrains, 2 different crater type terrains on Charon. One's a heavily cratered surface, which again dates back to the beginning of solar system history. And then there is a much less cratered plains called Vulcan Planum, which has some craters on it. And you might think it's a lot younger, but the reality is it's probably only maybe 1 billion years younger at most, or 500 million years younger. I mean, it's much the same way that when you look through a telescope and look at the Earth's moon and you look at the dark patches, the mare, and they have so many less craters on them than the highlands do, that you think, well, they have to be much, much younger. But the reality is that the lunar mare themselves are also very old. They date back to the first fourth of solar system history. The one thing that really surprised everybody was the lack of many, many very small craters. And the implications of that is that unlike the asteroid belt and the things which have hit the Earth and still continue to hit the Earth, there isn't just some parallel distribution of ever more numerous smaller and smaller things. As you get smaller, you get more and more of them. That there seems to be a roll-off, that there is only so many smaller things relative to the larger things. There's a shortage of them compared to similar populations of small things in the inner solar system. And we got sort of a hint that that might be the case when we started looking for our next target for New Horizons to fly to. We had anticipated we'd be able to easily find something between 5 and 6 targets to traverse, and we weren't finding them. We finally had to, in fact, use the Hubble telescope to find even 2 targets we could possibly go to, and we began to go back and look at what the statistical implications of this lack of smaller targets to fly to fits in nicely with the idea there simply aren't a lot of smaller objects, relatively speaking, in the Kuiper belt. Okay, here's Charon itself. The northern hemisphere is mostly dominated by this very rugged terrain. This, again, has been color-coded by elevation using we derived the topography using the means I discussed earlier of stereo images. The northern hemisphere is much more cratered. We're calling it Oz Terra. It is crisscrossed by very deep and very large fracture system, which form these big belts of canyons that are 5 miles deep, things like that. And then it gives way once you cross the equator, which is about here, to Vulcan Planum, which is relatively smoother and relatively less cratered. But even Vulcan Planum has some interesting surprises. Here is a color image, and this box here fits across this scene here. But in this higher resolution view, I want to point out a few things. We see these interesting isolated mountains, like Kuiper Mons here, which is surrounded by a moat. And here we see just a moat without anything in it. And this was a tremendous puzzle. It looked like somebody taken a brick and dropped it into Play-Doh or something. And we were having a hard time understanding what was going on. But when you look at things in stereo, and where we have topographic information, we can see that also the flow front here or the periphery of Vulcan Planum also bends downward, becomes lower elevation as it approaches the rim of this fracture system. And here's the Clark Montes, which also show that there's a moat of sorts around them. We think probably, or we speculate what may have happened, is that Vulcan Planum was formed by a very viscous water or some volatile icy material flow that flowed out. And because it's so viscous, as it approached its final resting place, that you had large lobate lobes which just sort of stopped. And likewise, we suspect things like Kuiper Mons, for instance, are blocks of this crust up here that broke, tilted, and foundered as this surface was being formed. And the moats are also formed just by the thick viscous flows sort of stopping as they approach things like these isolated blocks. And we can see some other things out on the surface. We see things that look like pancakes, and we see interesting fractures that remind us of lunar rills. There's a really weird little etched surface going on here. So we suspect that we are looking at some kind of some exotic ice, probably, or perhaps I should say, a mixture of ammonia and water that erupted on the surface and formed this surface. Reason we think it might be ammonia is that we do see, unlike on Pluto, we do see a few craters, where the craters have thrown out fresh material. We see ammonia ice in the fresh materials. And we do know that if you add ammonia and water together, it suppresses the melting point of water by 100 degrees Celsius. So that being the case, we could imagine that early in Charon's history that a water-ammonia slurries came out and formed this landscape. Okay, I told you I mentioned also the 4 little moons. These are the best pictures we took of them. As you can see, Nix and Hydra, which we discovered 10 years before we discovered Styx and Kerberos. It's easy to see why we discovered them first. They're much bigger. Here's a scale bar about 25 miles across. The only one we flew really close enough to see more detail on was we got Nix in color here. And we also got a view of Nix close up. And at this close-up image, you can see that Nix is fractured. And so it's almost the only object other than doing some crater counting on that we can say much about how it has been evolving over time. Okay, I want to begin to end my talk with this great picture. So this looks like a painting somebody's recently done of Sputnik Planum, the shore of Sputnik Planum. But this is in fact a painting done in 1961 by the great mid-20th century space artist Chesley Bonestell, who was a Bay Area native. And many of you, especially people here my age, remember a lot of Bonestell's famous books from the 1940s and 50s and 60s, like The Conquest of Space and so on. And I have to say, there's more. He has more pictures of things which he could not have had any idea what they were going to really look like. That he hits pretty much right on. And so when I was thumbing through my collection of Bonestell paintings and saw this one, I thought that's going to have to be the slide of the talk. So I want to share Chesley Bonestell, visionary before his time, 1961, amazing. Okay, so on to our next Kuiper Belt target, which will arrive, closest approach will be on New Year's Day of 2019. So all of you please stay tuned for the developments, and we will tell you what we find when we get there. And at that, I'll end the formal presentation and take questions.
I'll just stick with one. We never saw a spectra of water ice through Hubble or any other observations, and then LISA found the water ice. So what is so much better about LISA, and what does that tell us about our ground instruments?
Well, it's a heck of a lot closer. We were like 10,000 kilometers away from Pluto with LISA, whereas observations, from the Earth are, 32 AU away. So the smallest thing you can see on Pluto from the Earth is maybe 200 miles across, and the little patches of water ice that are peeking through the veneer of the more volatile ices and the tholins and the other materials which colorize Pluto are simply too small to make a signal as seen from the Earth.
Thanks.
Sir?
Yeah, thanks for coming out tonight.
Sure.
If you could, somehow throw New Horizons in reverse, what would be your favorite thing to go back and see and investigate a little bit more?
Oh, that's easy. I'd go see the other 2 hemispheres that we skipped.
Yeah.
I'd look at the sub-Charon hemisphere of Pluto and the anti-Pluto hemisphere of Charon.
And then, if you don't mind a follow-up, what do you expect to see in the smaller object that will?
Well, that's a good question. I mean, I don't think we should just, think, oh, well, it's going to be 25 or 30 miles across. It's going to be just some, battered lump that looks like something from the asteroid belt. It's so far out there, and in addition to the fact there seems to be a relatively small amount of small objects which can run into it, it could have primordial textures from the dawn of the formation of the solar system, and the composition of it could represent the deep freeze volatile materials which made up the initial materials which went to form the solar system. So it's our best kept in the deep freeze sample of early solar system stuff. Hasn't been processed, probably just sitting out there telling us how they ever came together in the first place. And at this point, we're reticent to speculate on what the surface may look like or what kind of materials we'll find. We'll certainly compare the chemistry of it with the chemistry of comets that have been measured by Rosetta and other spacecraft and see are we seeing the same chemicals, or are the chemicals on comets we've seen near the sun being processed? They probably are. So what do they look like in their primordial unmelted, unheated state? We hope to find out.
Thank you.
Sir.
Thank you for a very informative talk, Jeff. Was wondering if you could comment on how the team came up with a lot of the pretty cool, interesting names for these features.
Well, we have a colleague who works at the SETI Institute named Mark Showalter, who in fact gave a talk to this very group last year before the encounter. who is familiar with the process, the formal process that's used to derive names for surface features on objects in the solar system. And so using basically the guidelines of the International Astronomical Union, which historically has provided guidance on naming features in the solar system, we took a list and we then vetted it via a public website that the SETI Institute managed for us, and asked people to vote on what they liked as their favorite names, restricted to the list that was appropriate for the topics. And then that list was ranked in order by how votes went on it, and we simply started at the top of the list and went down as we began to name things.
Thank you.
So, were there any similarities between the surface features you saw on Pluto and other surface features in the solar system, perhaps moons of the giant planets, or was pretty much everything new in terms of surface features?
We'll certainly recognize some things right away. Recognize fracture systems, recognize craters. We recognized valleys right away. We weren't expecting to see them, but when we saw them, we began to ask ourselves, what the heck forms valleys on Pluto? I can speak for myself and say I wasn't ready or expecting to see large pools of solid nitrogen, and that solid nitrogen would be slowly convecting and forming blisters on the surface, or that it would flow across the surface as glaciers and carve out the landscape. That was a surprise. I did expect to see things like evidence for sublimation, where scarps would retreat and you'd have funny eroded features due to sublimation. That was anticipated. But the details of what we would see, we didn't really have any idea. And we were really surprised by Charon. We assumed Charon would just be some kind of boring cratered ball. The fact it has these big fracture systems and this southern plain Vulcan platinum, that turned out to be a surprise to us.
And with what you know now, would you characterize Pluto still as having a solid surface, or is it more, floating, moving around more than you'd expect?
Well, much of it's a solid surface. And in fact, if you were in a spacesuit, you could walk out across Sputnik Planum. Just because Sputnik Planum is made of relatively soft ice, you wouldn't sink in it. You could walk across it. But it is in fact stronger than silly putty. But silly putty is a good way to think about its mechanical behavior or its physical properties. It's like a stronger silly putty. It's less strong than glacial ice is on the Earth, but it is stronger than silly putty.
Thank you.
I'll assume that the spacecraft has to make course corrections on the way, and if so, how does it know where it is?
It knows where it is by several means. We track it, of course, from the Earth, from this radio signal. It has star trackers on it that gives its position in the sky. So the combination of being able to detect it from its radio signal and knowing its position in the sky based upon its own internal star trackers, we can figure out where it is at any given moment. And we basically hone in on the target by taking lots of pictures of the thing we're flying towards, doing calculations about how close are we to the aim point we want to hit, and if we need to change things, we burn a little bit of propellant to change the course.
Thank you.
Sure.
Hi. Is there a reason that all of the water ice is mainly on Sputnik Planum?
Oh, the water ice is only on Sputnik Planum where it's floating as big blocks. But the whole rest of the crust of Pluto is probably mostly made of water ice. You might have to dig down a bit to get to it, but all the highlands and the mountains and the craters and things you saw that are not Sputnik Planum, they're probably mostly made of water ice, or being held up by water ice.
Thank you.
Sure.
My sense from other sources, I think, is that the object you're going to encounter in early 2019 is about the size of Nix, say, give or take.
Yeah.
Can you talk a little bit about how you're planning for that encounter? Do you know how close you can get to it without being so close that the images are streaky and things like that?
Well, we, in fact, are planning that right now. We had to plan that for our extended mission proposal, and we hope we can fly close enough to see things as small as 20 meters across. So that's 10 times better than the best picture we took of Nix, for instance.
How close would the spacecraft be then to that object?
I think it's, what the number is again, I think it's maybe 1,000 or 2,000 kilometers away.
Thank you.
That's still being determined. We're working out what are our best options.
I have kind of a two-part question. Are there any sign of silicon or other rocks on the surface? And I guess my follow-up is, reading from one of the diagrams here, it's talking about how the atoms in our body were created 8 billion years ago or something like that, or possibly beyond the age of the solar system. So my question is what is the largest, if an atom in my body was created before the age of the solar system, then what is the largest size chunk of something that survived from another solar system? Is it just an atom? Is this too much of a complicated question? For
Well,
example, is
it's
there
actually a
rock?
question you should ask your April speaker, but I'll take a little bit of a shot. Let me ask you your first question first. That's easy. We don't see any silicates on the surface of Pluto, although we think that silicate rock makes up much of its interior, as I showed in that one slide. We think that the heavier elements are formed by supernova explosions, and they were supernova which exploded before the present solar system, the sun and the planets were formed. So this stuff was out in the form of nebular clouds in our galaxy, which came together to form the solar system and incorporated these heavy elements which make up us. And while there is speculation on how much interstellar dust there is, and there are other people in the audience, including a person who asked me a question a moment ago, who could answer that question better than I can. And you should certainly save that question for your April speaker, but it's safe to say that very probably the heavier elements which make up our bodies, like the iron in our hemoglobin and the calcium in our bones, are formed by supernova explosions which took place like 8 billion years ago. And it's probably safe to say they're obviously here as atoms and molecules, and whether they survive in bigger chunks or not, I don't know.
Thank you.
Sure, thank you.
Yeah, real quick. Why did Sputnik Planum seem to feature such a variety of compounds and molecules, while the rest of the pictures that we saw seem to have an individual or like one featured compound or molecule?
Well, Sputnik Planum, as you can see, is bright. And in space, especially where there isn't a very substantial atmosphere, bright means cold because it's reflecting what little sunlight it's getting back into space. So it's a cold surface, so any gas, and even small amounts that are floating around in the atmosphere, is going to tend to want to freeze out onto Sputnik Planum. So for a variety of reasons, we think that Sputnik Planum is mostly made of nitrogen ice. It's the only place we see any carbon monoxide ice. Carbon monoxide, the ice, has almost the same properties as nitrogen ice. It has about the same density. It freezes about the same temperature, and so on. So we can imagine that Sputnik Planum is mostly nitrogen ice with some mixture of carbon monoxide ice in it. But because it's cold, you're also going to get local frosts of methane, and so that's why you also see a methane signature.
Thank you.
I don't know a lot about geology, but I'm wondering about the radioactive elements that you talked about, and wondering if there's a natural process that replenishes those, or whether it's a finite supply and just decaying away, in which case at one point it would have been a lot warmer and a lot more fluid on the surface because it had a much higher amount of material, radioactive material.
Radioactive material is funny, but yes, to 0th order, it's correct to think of it that you have more stuff that's there in the past than there is today, because it's obviously decaying away. Its half-lives are very long, and over millions and billions of years, you've gone from the more radioactive, more energetic element or species of the element to a form of the element or its daughter elements, which are either not radioactive or less radioactive. So the trend would be for things to have been warmer in the past from this process and cooler now. I mean, the same thing's happening to the Earth. To the extent the Earth's interior is still being heated by radioactive elements, it was doing a better job of it 3 billion years ago than it is today.
Thank you.
Are there plans for future missions to Pluto, and also what would be involved in getting a probe on the surface of Pluto, as, say, we do on Mars?
There are no current plans to go back to Pluto, although I think people at this point are beginning to think about if that's possible. Pluto is a challenging place to go to. It's very far away. It's about 35 times further from the sun than the Earth is. And we took the strategy that we would go out there quickly. By quickly, it took us 10 years to get there. And while we were there, we flew past it very fast. We flew past it 10 miles a second. We had to build a spacecraft to take a lot of data very quickly during the few hours we were near Pluto, which is what we did. But the problem is, by traveling so fast past Pluto, you'd have to launch a rocket about the same size as the rocket we used to launch it in the first place, with your rocket to fire the engines to slow it down to get it into orbit or land on the surface of Pluto. So there are technologies. It's not technologically impossible to build a spacecraft that could, travel to Pluto and go in orbit around it. It would probably have to be powered by large nuclear reactors and probably be ion engines, and you'd fly halfway out to Pluto and turn around and then decelerate into an orbit around Pluto. And that probably, if you wish to spend the money and the time and technology and the political coin to make that happen, probably build a spacecraft, get there in 10 or 20 years. And of course, once you did that, once you're in orbit around Pluto and Charon, it would be relatively easy to deploy landers and rovers down to the surface. And again, there's no fundamental aspect of physics which would prevent us from doing that. Or for that matter, it's technically imaginable even today to do that. It just requires, as Dr. Strangelove would say, merely the will to do so.
Why is it that you see a significant amount of carbon monoxide ice on Pluto, but no carbon dioxide?
Well, carbon dioxide is a lot more refractory. That's probably too big a word. It's much less volatile than carbon monoxide ice is. And so it would freeze out at much higher temperatures than carbon monoxide does. And so it wouldn't really be mobile. It would be, if it existed at all, it would have properties more like the water ice rock than it does, the water ice, which acts like a basement rock, than it would as any of the volatiles.
Well, you do see water ice, so why wouldn't you see carbon dioxide ice also?
Well, there was some speculation we might see carbon dioxide ice, and we don't. There are chemical arguments that people can imagine explanations for why you don't see carbon dioxide ice. But it's a situation where there was no reason to think it might not be there, but we haven't seen it yet. So if it's there, it's in small amounts.
Okay, thanks.
Yes, ma'am.
I have another question. What's your biggest question about Pluto?
My biggest question, goodness. I guess at this point, I'm wondering, how do those things which look like volcanoes get there? That's what really has me scratching my head. That's a hard one to explain.
Would those volcanoes be able to erupt?
I'm sorry, say again?
Would those volcanoes be able to erupt from all the way up Pluto?
Well, we didn't think so, but again, we're going to have to think about what the heck made those funny mountains with holes in the middle.
Would the volcanoes be hot, or would they be cold?
Well, they wouldn't be any hotter than freezing water at most. So the hottest thing on Pluto that you could possibly imagine would be 32 degrees Fahrenheit.
Thank you.
You're welcome. And that would be very hot because Pluto's surface is about minus 370 degrees Fahrenheit, 40 degrees K.
Just two quick questions. When you measure the topography, the heights, on the Earth it's the sea level. What do you use as a reference level on Pluto?
Well, we're still actually working what we're going to use for our reference level, so we usually simply refer to as the local scene. So within a scene, what's the dynamic range of topographic elevations? And so the lowest thing we assign it a value of 0, and the highest thing is whatever that is in kilometers above the lowest thing we see. But we are working on an attempt to come up with a better understanding of the geodesy of Pluto, and that's something we will need to get our hands around. It's not easy to do. The people who are working on it are making slow but hopefully steady progress.
Okay, and the second question, for the benefit of people who may not be astronomers or geologists, you mentioned the word tholins. Can you just define what that is?
Yes, I'm sorry, I should have mentioned earlier. Well, so as you remember, I showed you some very dark and dark reddish patches on Pluto, especially around the equator, like the Cthulhu Regio I mentioned earlier. We think this agent, the material, the darkening agent, is tholins. And tholins is actually a name I think Carl Sagan invented back in the 1980s when he was first thinking about Titan, which is a large atmosphere-surrounded moon of Saturn. And tholins are thought to be made, and certainly Carl Sagan and his laboratory assistant, Bisham Carey, who lived here in the Bay Area just a few years ago when he passed away, could make them in the laboratory by taking methane and irradiating it in other gases, and it would produce slowly but surely, like the old Miller-Urey experiment, you would make dark gunk. And so tholins is a variant on the dark gunk that or dark organic gunk people can make, and it's probably those layers of haze I showed you in the high phase view of the crescent of Pluto. Well, that's the beginnings of tholin. The hazy stuff eventually settles out, collects, and stains the surface.
Thank you very much.
Two more questions.
Okay, Kate. Then let's take this one, and then yours, sir.
You'd mentioned that you were interested in what was on the other side, and we did get a glimpse of that during the approach, the whale. I'm just curious if you have some speculation of what the whale is.
Well, as it turns out, the head of the whale is Cthulhu Regio. So you can see like the first third of the whale, that's what's making up that dark feature you see along the equator on the western part of the encounter hemisphere, and then the whale's tail wraps around the back where we can't see it, and then there's a series of other dark spots, of which one of those dark spots you can see just to the southeast of Sputnik Planum, and we think the dark spots are tholins. We think the reason the dark spots are limited to the equator is because the equator is the only place where you always have a day-night cycle. You never go through long periods of time where the sun doesn't shine for many, many years at a time. And so we think there's a predisposition for dark stuff to form and collect there. But what kind of landscapes it's forming on, there's some suggestions that some of those are elevated plateaus and other places might be large depressions, and we're still trying to sort out what the heck is going on. Pluto is very heterogeneous. I think there's a good argument that we could afford it and proceed with another mission there. I think everybody would be very excited to see what else is there. Huh?
Good reason to go back.
Yes, we'd love to go back. So I think we've just scratched the surface. So I think there's a lot of stuff going on in Pluto that we haven't seen examples of because it was in the dark or it was on the other side of the planet.
So you gathered a lot of data as you approached and as you receded, and are you saying that data is still being downloaded? Do you see any surprises coming, and when will all that data be finally assembled?
Well, most of the imaging data has arrived, although we still get a few images down. In fact, a few images came down over the last few days. But 95% of the geologically useful imaging data has been sent down to the surface, at least in losslessly compressed form. What really hasn't come to the surface yet, just because it's hard to compress, are a lot of the spectral data, a lot of the multispectral imaging from LISA. Those data don't compress very well, and so we should learn a lot more about the composition of the surface of Pluto and Charon from the data, which will come down over the next few months. And then we'll replay everything again without any compression whatsoever, although lossless compression probably won't make much difference, I don't think. And so we should probably finish reading out the data from the encounter itself by the end of this year. All right, thank you, everybody.
Thank you for a wonderful tour.
My pleasure.
Yeah. All right, everyone, please drive carefully, and we'll see you in April.